Hello class, I'm Professor Pat, and today we will be talking about continuity and one-sided limits. So what are we going to be talking about today? Well, first we're going to talk about continuity at a point, continuity over an open interval, then we'll touch on discontinuity. So we'll get one-sided limits. After one-sided limits, we'll talk about continuity over a closed interval, properties of continuous functions, and the intermediate values theorem. So, imagine a function f. If there are no interruptions in the graph at the point f of c, we would say that the function is continuous at x equals c. If a function is continuous at x of c, we can clearly see there are no holes, jumps, or gaps at that point in the graph. There are three circumstances which will make f of x not continuous at the point fc. One of these circumstances will be if the point f of c is not defined. Another will be if the limit of f of x as x approaches c does not exist. And the third and final circumstance which will make a function discontinuous would be if the limit of f of x as x approaches c is not equal to f of c. Denoted clearly here in this graph with a jump. So if none of these three circumstances are met, then we know that our function is continuous at the point c. Let's talk about an open interval. If a function f is continuous at every point in the interval ab, the open interval ab, then we know the function is continuous over that interval. If the function is continuous from negative infinity to positive infinity, then the function is considered everywhere continuous. For example, this function, f of x equals x squared, is everywhere continuous. So, if an interval I that includes point c, a function f, is defined on I, and f is not continuous at c, then f is said to have a discontinuity at x equals c. A discontinuity at c is removable when f can be made continuous by appropriately defining or redefining f of c, and discontinuity is non-removable when the limit of f of x as x approaches c does not exist. So, we determined we've got three cases of discontinuous functions right here, and we're going to determine if each function has a removable or non-removable discontinuity. So looking at our first example here, we could see that visually f of x appears continuous. However, there's a hole in the graph at the point c. So if we define c, this point at c, then f of x will be continuous over this open interval, making this a removable discontinuity. In our next option, we noticed that coming from one direction and from another direction, our values as x approaches c are indeterminate. Therefore, this discontinuity is non-removable. However, in our third case here, if we were to redefine f of c, it would make it f of x continuous at point c. Making this a removable discontinuity. Okay, so you noticed I said the limit does not exist? Well, we're talking about limits from both sides. You need to talk about first limits from one side. So we've got a right-handed limit, or a limit from the right, meaning that x approaches c from values greater than c, is denoted by the limit of f of x as x approaches c with a little plus right here. Alternatively, a left-handed limit where x approaches c from values lower than left or smaller than c from the left. That limit is denoted as the limit of f of x as x approaches c with a minus up top. Can be said as limit of f of x as x approaches c from the right, or the limit of f of x as x approaches c from the left. So consider this function, f of x equals the square root of 4 minus x squared. Determine the limit of f of x as x approaches -2 from the right. So it is denoted by the limit of f of x as x approaches -2 with a plus sign. So graphically looking at it, as the x value reaches -2 from values greater than -2, we notice that f of x is approaching 0. We can also determine this algebraically using direct substitution. If we put -2 in for x, we get 4 minus -2 squared, which would be 4 minus 4, which is 0. So, let f be a function, and let c and l be real numbers. The limit of f of x as x approaches c is L, if and only if the limit of f of x as x approaches c from the right and the limit of f of x as x approaches c from the left are both equal to L. If that is not the case, the limit does not exist. Alright, let's talk continuity on a closed interval. So consider this function, f of x equals the square root of 1 minus x squared on the closed interval -1 to 1. Visually, looking at this graph, you can clearly see that this function is continuous on the closed interval -1, 1. And additionally, we can tell that the limit as x approaches -1 from the right of 1 minus x squared equals 0. Notice f of -1 also equals 0. The same can be said about the limit as x approaches 1 from the left. We'll get f of x equal to 0. The limit equal to 0, as well as f of 1 is equal to 0. So therefore we know the limit, this function is continuous on this closed interval. So, if b is a real number, f and g are continuous at x equals c, then a scalar multiplication such as b of f, a sum or a difference, f plus g, f minus g, a product, f times g, will all be continuous at point c. A quotient, f over g, will also be continuous at point c, given that g of c is not equal to 0. So the continuity of a composite function theorem states that if g is continuous at c and f is continuous at g of c, then the composite function f of g of x is continuous at point c. Alright, now we need to talk about the intermediate values theorem. The intermediate values theorem states if the function f is continuous on the closed interval a, b, and f of a does not equal f of b, and k is any number between f of a and f of b, then there is at least one number c in a, b, the closed interval, such that f of c is equal to k. A function that is not continuous will not necessarily exhibit the intermediate values property. So, using the intermediate values theorem, we can determine the zeros of a function that is continuous on a closed interval. If the function is continuous on the closed interval ab, and f of a and f of b differ in sign, then the intermediate value theorem guarantees the existence of at least one zero of f of x in the closed interval ab. Any questions?